Okay, welcome everyone to the Global NCG Seminar today. So our speaker today is Jinmin Wang, based at Beijing. So, so today Jinmin is going to tell us about his work on Coarse Baum conjecture for LQ coarsely embeddable spaces. So please, Jinmin.
Uh, Thank you, Professor Tang, for your introduction and invitation. It's very nice to give a talk here. So today I'm gonna talk about work done with Zhizhang Xie, Yu, and Boju on coarse Baum conjecture for spaces that coarsely embed L2. Okay, so in this talk, I will first give an introduction to the so-called coarse Baum conjecture. And I will introduce our main tool to study this conjecture. We are using a Dirac method, but related to the LQ space. And I will sketch the proof a little bit. And if we have enough time, I will talk about another application of a method to prove an LP version of this conjecture. All right, so let me start from the introduction part. So the motivation of studying this kind of coarse Baum conjecture is to do the index theory for non-compact manifolds. So let's start from X being a non-compact complete spin manifold. Well, spin is not very important. And we want to do index theory on this non-compact manifold for example, the Dirac operator. So this is a canonically first order self-adjoint elliptic differential operator that acting on the Hilbert space of L2 sections of the spinor bundle. So this is a self-adjoint operator, so we can define its functional calculus. So let's consider its normalization, like F is equal to like D over square root 1 plus D squared. This is a bounded operator. And we can see that F squared minus 1 is minus 1 over D1 plus D squared. And those are all bounded operators in B of H. If X is compact, then this guy, F squared minus 1, is a compact operator. So it's Fredholm, then we can do Euro Fredholm index. However, if the space is non-compact, this operator is no longer Fredholm. But it's still invertible modulo system algebra A, which contains this kind of operators, the functional calculus of D, where this F lies in C0 of R. Here, this example, minus 1 over 1 plus X squared. Okay. So in this case, if F is invertible modulo system algebra, it defines the key theory class in the key theory of system algebra. This can be regarded as a generalized Fredholm operator. So the problem is to choose the nice A. But the A has to be very perfectly chosen. If it's too large, like the B of H, entire B of H, then the key theory is trivial. There's no interesting information. If it's too small, like equal to this space, the generated by F of D, it's too small to compute its key theory. So the perfect candidate should be something in between, not too large, not too small. So we need a nice candidate of it. So we want some featured properties of these operators, F of D. So these operators have two very important properties. So first, it's called locally compact. Namely, if we have this operator multiplied by some compactly supported characteristic function, then it becomes a compact operator. This follows from the classical Rayleigh lemma. You know, on compact domains, this kind of functional calculus is a compact operator. So it's not necessarily compact, but only locally compact. And another important feature of this operator is that it's has finite propagation. So we can use the Fourier inverse transform to see that. So F of D is equal to the integral of F hat psi. This is a Fourier transform times e to the I psi d. So this e to the I psi d is a wave operator. And so you can imagine it just to be the fundamental solution of the wave, just as the wave we have seen in real life. And in particular for a wave, if like drop a stone into the lake, the wave will propagate only at a finite distance for finite time. But for these functions, we can assume this f hat has compact support. All such functions are dense in C0 of R. So now Kasai is supporting a compact set, meaning finite time. So this operator will propagate only at a finite distance. So approximately all FD has finite propagation. So these two featured properties actually give us a nice candidate of this system algebra. This is the system algebra introduced by John Rowe, so-called Rowe's algebra. So let's start from a Hilbert space, which is a C0x module. And we call it a geometric C0x module if we satisfy the following condition, that this module is non-degenerate and any non-zero f act as a non-compact operator. So we want this module action to be ample enough. So for example, if x is discrete, you can just take this x to be L2 of x tensor a Hilbert space. The second component is to make it ample enough so that no operator act on compact. And the second example is that for any x, you can take a countable dense subset Z, and then consider the L2 of Z tensor L2 of N. So we will use this example many times. And another example is that for like when X is a complete Riemannian manifold, you can use capital L2. So this is related to the example I've told you before for index theory there. Now we can define this. Oh, sorry, is there any question? Okay. Now we can have the definition of Rowe algebra to be the operator that acts on this Hilbert space that is locally compact and has finite propagation. So here we mean locally compact by multiply the operator by a compact supported function, then it becomes compact. And propagation smaller than R, meaning that if you multiply by operator with two functions f and g, that their supports are far away, then it becomes zero. So roughly speaking, you start from a stone at G and propagate like using a wave of T, and it will not touch the supporter of F. So then, namely, this operator entirely becomes zero. Okay, so one example of this algebra is operator generated by the index of Dirac operators. Another example is that when we think X is just a discrete space, and we can take H to be the small L2X times the small L2 N I just told you, then we can consider the elements in the Rowe algebras as matrices. T is Txy, where Xy is in X. Then this operator is locally compact, meaning that each component is just a compact. It has propagation smaller than R, meaning that Xy is greater than R, then the component is zero. So a picture of such operator is like this. So if X is in X, Y in X, then this operator is only supported near the diagonal, where this length is roughly speaking R. And then we take completion of all such operators becomes the Rowe algebra. So the Rowe algebra is something that reflects the large scale geometry of X. It neglects small scale, but only look at large scale behavior. And as I told you in the example, if you consider X as a complete Riemannian manifold, then the index of, like, for example, a Dirac operator lies in the case area of Rowe algebra. Okay. So we want to understand the index of a Dirac operator. Then we need to know, at least we need to know what is this case area. So the problem is to compute the key theory of this C-star algebra. So this is computed by so-called Coarse Baum conjecture. Okay, so let's take X to be a discrete metric space with bounded geometry. For any scale d greater than 0, we can define a Rips complex PD of X to be a simplicial complex whose vertex set is X. And okay, this should be tuple. I should say, I just rewrite this part. So if K in X forms a simplex, if diameter of K is less than or equal to D. So maybe let me quickly draw you a picture. So suppose X is some discrete points, okay? And if points are close enough, then we connect them by edges. If the triangle is smaller than enough, then we can fill in this triangle or fill in this triangle. But if they're very far away, then we just ignore it. Okay. And after this, for each fixed D, it becomes a simplicial finite dimensional simplicial complex. So this Rips complex actually also reflects the coarse geometry of X because it also neglects small scale. So for example, you can imagine if X is a manifold that has a hole, then when D is large enough, larger than the hole, it will fill in the hole. Okay, so conjecturally, this space should also reflect the coarse geometry, so it should be related to the key theory of the row algebra. And this is so-called Coarse Baum conjecture that this mu, we'll call it assembly map, that maps this key homology of the Rips complex when D go to infinity to the key theory of row algebra is an isomorphism. So roughly speaking, the key homology of a space is the spin state, all possible spin state Dirac operators on it. Then this assembly map is roughly speaking taking the generalized Fredholm index of a spin state Dirac operator, which lending the key theory of the row algebra. So this conjecture is very good because the left-hand side is usually computable, but right-hand side is unknown. So let me give you an example where the left-hand side is known. If X is equal to M tilde, where M tilde is closed manifold, and also a K pair 1 space, namely all its higher homotopy groups vanish except pi 1, then the left-hand side is just a group of integers generated by the K homology of the Dirac operator on X. So yeah, it's very simple. But the right-hand side, if the conjecture holds, then we know that right-hand side is also an integer. And if we know this mu is injective, this means that this integer generator will not be killed in the row algebra. This actually implies the so-called Gromov-Lawson-Rosenberg conjecture, saying that on this manifold, this kind of universal cover of closed K pi 1, if mu is injective, the conjecture is that for this space, there's no positive scalar curvature. So if mu injective, then it supplies this conjecture. But if we furthermore know that mu is isomorphism, then it follows by a so-called descent principle of drawing row. It tells us a strong Novikov conjecture for discrete groups. So namely that we will start from a space without any group. But if you know the mu is isomorphism, we can go back to the classical form conjecture for groups by taking X is equal to the Kelly graph of the group gamma. And in this case, we can know the original strong Novikov conjecture. All right, so now the problem is to study the assembly map mu. It was suggested by Gromov that this kind of map, this kind of conjecture is related to the so-called coarse embeddability of the space. So suppose that you have a metric space X and another metric space Y. If there's a map X to Y such that the distance in Y of 2 points is controlled by some upper and lower bounds of the original distance in X, then we say that this X causally embed into Y. Here, this rho minus and rho plus are two functions, non-decreasing, and its infinity as infinity. So it's an upper, so roughly speaking, we have an upper and lower bound control of the distance of the image. So for example, if they're linear, then this is just a by Lipschitz embedding. But in general, it can be nonlinear. It can even be not continuous. And there's a very nice, very beautiful result of Guoliang Yu in 2000, showing that if X causally embed into a Hilbert space, then our mu is an isomorphism. And then it proved by Xiaoman Chen, Qin Wang, and Guoliang Yu that if X is causally embedded to a Banach space with so-called property H, I'm not going to explain the definition, but keep in mind, have in mind that this space, LQ of n, for Q is in 1 to infinity, is an example of a Banach space with property H. And they have shown that for this space, mu is injective. But however, unfortunately, this conjecture is false in full generality. There's an example of Willy Yu that if X is an expander with large curves, so roughly speaking, we have it's an expander that contains very large circles. In this case, mu is injective, but not surjective. Well, the conjecture actually holds for some kind of relative expanders, but for this special expanders, it's not true. But because this X is an expander, it does not causally embed into the LQ space. Well, actually, it cannot causally embed in any uniformly convex Banach space. So it will be a natural question that is there any nice example of spaces that where the surjectivity fails? So here we only find some bad examples, standards. But what about in this case? Like, can we find some spaces that still causally embed into a nice Banach space, but the conjecture fails? Okay, like here we have injective, but can we show the surjective part for this result? So this is our main result, saying that if X is a discrete matrix bounded geometry, and if X causally embed into LQ for some Q in 2 to infinity, then we can prove not only the injective part, but also the surjective part. Then the entire map is the isomorphism. Okay, let me give you some quick remarks. So here I've said that Q from 2 to infinity. But we neglect the small q's because it's a result of Nowak that the cost embedded into L2 and the small q's, they're actually the same. So we don't have to worry about small q's. Just look at our large q's. But for large q's, our result is actually at least logically stronger than the Guoliang result for Hilbert space. because causally embed into L2 implies causally embed into LQ, but not vice versa. In fact, the LQ space cannot causally embed to L2 for large Q. And also, as a corollary, by the distance principle, our result implies that the Stronovikov conjecture for groups that causally embeddable into LQ space. This actually is already a known result of Kasparov earlier, but here our proof actually gives another understanding of why this is true, because the Coarse version is correct, then it implies the group version, Stronovikov conjecture. Okay, so here's a brief introduction and the description of the main result. So any questions? Okay, so let me just briefly talk a little bit about this kind of difficulty of this conjecture. So we want to understand the key theory of the C-star algebra, the row algebra. But the difficulty is that this C-star algebra contains only very bad ideals. Well, it has some ideals, but ideals inside this algebra cannot separate points. Well, if you have 2 points in X, and we want, if you have 2 points X and Y, if you can find a nice ideal that separates the 2 points, that contains operator localized at X but away from Y, then you're done. Then you can prove the theorem by like Navier-Torres argument. However, for row algebra, it contains only finite propagation elements, but the propagation can be very, very large. So that for any 2 points, you cannot separate it. So the key idea of proving this result is to find nice ideals that localize the Zemin map or the row algebra to 1 point and neglect the other. Okay. Or in other words, to separate points. So keep in mind this idea, and let's see how do we separate points by constructing ideals. Our main ingredient is a Bott-Dirac operator. Here, our operator is constructed from the LQ metric, but still it acts on the Hilbert space. So we need something to relate LQ and L2. And this relation is established by the so-called Mazel map. Let's say E is a finite dimensional vector space. On this space, we have many metrics, LP, LQ, or infinity, whatever, they're all equivalent. But here we're specifically looking at L2 and LQ. Let's define a map small psi. So it maps x1 to xn to this form. So roughly speaking, it's just x1 to the q over 2 with a sign there. Okay. And with this explicit construction, we can say that if you look at the psi of V, its L2 norm square is summation of xi to the q over 2 and then square. This is exactly summation of xi to the q. So it will be equal to the LQ norm of V to the q. Oh, well, this is exactly the first line I'm plotting here. So in particular, this map psi maps a unit sphere in LQ to unit sphere in L2. So then we can define the map capital psi that you have a vector V. Well, in E, you can imagine it in LQ, and you normalize it in the unit sphere, and do a psi, give you an element in the unit sphere of L2, and you multiply back by its LQ norm. So in this case, this capital psi is an isometry in this sense. Well, but it's not really an isometry because it's a nonlinear map. It only has geometry in this form. And another good feature of this map is that it's Lipschitz. And it's actually Lipschitz uniformly independent of dimension. This constant is dimension free. Okay, so this is super important. And now we can use this module map to define a Dirac operator. We're going to work on the Hilbert space HE to be the L2 differential forms over E. This is the Hilbert space. And on this space, we have a Clifford NN action with respect to a bilinear form that is sign one on first component of sign negative on the second component. And we want to define operator C sub V on this Hilbert space HE by the following. So you have a differential form. You do CV on this form at each U, meaning that you multiply omega by the Clifford action of this psi of U minus V. Okay, let me draw you a picture. So let's say this is E, this is a base point V. If you have any point U, you actually multiply it by this function. Well, this Clifford action. U minus V is just this, and this is and you do a capital psi it. This is the psi U minus V, and you multiply it by the multiply the Clifford action on it of it to the differential form. Okay, so this is an unbounded operator acting on this Hilbert space. And now we can define the Dirac operator to be S inverse D plus CV. Let me call it BSV, where D is just a de Rham operator, D plus D star, and CV is this operator above, centered at V. And our F to be the B over 1 square root 1 plus B squared. So let's compute the B squared. So if we square it, you get S inverse 2 D squared plus S inverse and the commutator of D and CV, and plus this CV squared. So C squared is equal to 1, and this gives us a norm of psi in the L2 norm, but by our construction is equal to the LQ norm. So the last term will be very large if U is away from V in LQ norm. Okay. But for the second term, remember I have told you that this capital psi is Lipschitz. So this is a commutator of D with a Lipschitz function. So it's actually bounded. So when S is very large, this guy together will be small. And the last term is very large. So with this observation, we have the following properties. So first, it's 1 minus F squared is 1 plus B squared inverse. It's a compact operator. This is because like when U is very away from V, the last term is very large. You take an inverse, it becomes small. So it's actually compact product in some sense. So because it's compact, the F is Fredholm, and we can compute the index is equal to 1. And also, as I show you, the last term is very large if U is away from V. So if you do an inverse, like here, it will be very small when U is away from V. So this means that approximately 1 minus F squared is very concentrated near V with respect to the LQ norm. So this is super important. Where you actually use the LQ to measure the concentratedness. And finally, we want to look at its propagation. So because this FSV is S inverse D plus CV, so we have S inverse here. So we can use the wave operator argument to show that like this F is approximately has propagation as inverse with respect to the L2 metric. But here is a very, very important fact that I think everyone knows when we are the undergraduate students, that the LQ metric, when Q is greater than 2, is actually smaller than the L2 metric. Okay. So by this very important fact, we can conclude that this F also has small propagation with respect to the LQ. So let's think about this. So propagation means that if you have 2 points far away, LQ far away, want to know that its value is 0, right? So if 2 points are LQ far away, then by this inequality, they are L2 far away. Because they are L2 far away, then the value will be 0. Because the first line, then, well, it's 0. So that's actually our conclusion. So to summarize, this operator F as V is actually very nice. So it will localize the operator, localize everything to the base near V, and also localize in the sense that it has small propagation with LQ. So although it's defined on the Hilbert space, but we're discussing these properties in the LQ metric. Okay, so now I can tell you roughly speaking how to really prove the theorem using this operator. So first step is so our construction of this F is actually on the finite dimensional vector space. So we have to reduce our discussion to a finite dimensional case. So we can decompose X into X1 union X2, where X is of this form. We can draw some annuluses, and let's say the other part will be the X1, and the other part will be X2. And we can assume that the distance of each annulus, each pair of annulus will be very, very far away, so that the discussion will be concentrated at each annulus. But each annulus is a finite set because it's discrete. So we can modify the embedding a little bit so that it costly embed into a finite dimensional vector space, E, with arithmetric. And the important thing is that here we are doing uniform row plus or minus. So this process really reduces the discussion to finite dimensional case. And then you can use the Mail-Victorious argument. So if you know X1, if you know X2, and also X1 intersect X2 is also of this form. So then you know everything. So this is actually a question of our approach. So we can only define an operator for finite dimensional vector space. And so we have to localize our distress to finite dimension. So it will be an initial question is that can we define this F as V for infinite dimensional? Directly. So because if you want to do like an equivalent case for groups, then you cannot do this kind of partition because it will destroy the group action. But if you can really define this F for SV for infinite dimensional, then you can probably prove the Wang conjecture. But there's still a kind of gap there, and as you can see, the definition of SV is a little bit complicated. It's highly nonlinear that involves the non-zero map. So it's still an open problem there, but it will be interesting to really find out how to do an infinite dimensional analysis of this kind of operator. Okay, but now for this coarse version, we can really localize, really specialize our discussion to finite dimensional case. Okay. So now let me tell you how to really directly prove it. So we start from the FSV, and because it's a Fredholm operator, it can define a canonically an idempotent, let me call it PSV, that represents its index in the compile operator. So the PSV is very explicit. You can use like the boundary map in the operator K theory to write it down. Okay. And so we start from an operator in the row algebra like TXY. So keep in mind what we're gonna do. We're gonna do like is the following. So you have a TXY here, and we'll multiply TXY with the extra P, where PS is this S here, is the propagation, and the base will be Fx. So for each TXY, we twist it by a ball Dirac operator that centered at Fx, where F is a coarse embedding. So we want to deal with operators like this. So actually, our definition is exactly the one to help make to define something that contains this thing. Okay, so we start from the Rips component PDX, and we use H to be L12Z times L12N as we discussed before. And now we consider an L algebra to be a collection of paths T sub S, and each S is a matrix TXY. This act on H tensor HE, where H is this space above, and HE is a Hilbert space on the finite dimensional vector space. So on this space, we actually have two actions, X action here and E action here. So you can define like propagation or locally compact in two different directions. So on the X direction, our requirement is the same as before. So it's uniformly bounded path, and it's locally compact, find the propagation in the X direction. But on the E direction, we're actually talking about this kind of operator, P as Fx. When S is very large, its propagation is like S inverse, so it go to 0. So this is our requirement. The E propagation go to 0 with respect to the LQ metric. So just keep in mind this our example here. And the second requirement, like we are considering operators based at Fx. So we want this operator to be supported near Fx with respect to LQ. So like this to say there exists some R that this operator acting on HE, like you can regard it as an integral operator that only supported both components supported near Fx. Okay, now we can complete all such passes and get an operator system algebra A, and we'll call it twisted row algebra. Okay, so we start from an element in the row algebra, and we do a twist, like I showed you before. Then this will be exactly an element in the A algebra. Then we evaluate at S equal to 1, let's say, and we'll land in it will land in an operator that acts on H tensor HE. But this is still an X module. It's a geometric C0X module. So this algebra actually, at least the key theoretical, is the same as the row algebra. So the first line and the last line, they are actually the same. So we expect that the composition of these maps should be the same. But actually, yes. This construction, this map actually defines or gives us a well-defined key theoretical map. So we start from an element in the row algebra, and the first step gives us a map beta, go to the key theory of the A algebra. Then evaluate it, gives us the element in this algebra, which is still the row algebra. And we can show that the composition of these two is equal to the identity. And now our proof of the Coarse Baum conjecture is it's concentrated here. For this A algebra, we can show that the Coarse Baum conjecture holds. Yeah, if this holds and this composition identity, then you do a diagram tracing, you can know the original Baum conjecture. Okay, so maybe let me just quickly tell you why this is true. Because for this A algebra, okay, maybe I skip a little bit. I do very quick on this page. For this A algebra, we can find very many rich ideals. Okay, I'm not going through the definition, but just want to tell you that for this algebra, there are very rich ideals that can localize our discussion to single points and separate points. So with this rich structure of ideals, we can prove the Baum conjecture of it. Okay, maybe I just want to skip this page so that skip this a little bit details to tell you a little bit of the of another interesting object. Maybe I have, I guess, 8 minutes. So maybe in the last 8 minutes, I want to tell you a little bit about another interesting problem of our approach. Okay, so far we were talking about the classical Coarse Baum conjecture, but you know it's also necessary to talk about the LP version of this row algebra. It's actually a little bit weird of our result. We start from a space that coarsely embedded to LQ, but we prove the Hilbert version of Baum. So maybe in your mind, we should prove the LQ version of Baum. But however, we first prove a Hilbert version, and we found out that our approach also applies for LP, for any P. But okay, but of course, the first problem is, what is the LP Baum or LP row algebra? So we still start from a metric space, and let's look at a Banach space X, a so-called geometric LP X module. So maybe I let me do not tell you what it is, but this is just a Banach space and LP space with a C0X action. And on it, you can define the propagation and locally compact and so on and so forth. And you command the row algebra to be the operator of locally compact finite propagation. And then you can define a row algebra to be its completion in this operator space. And we can formalize the LP Coarse Baum conjecture. You start from the same K homology and map to this Banach algebra. Okay. So what is this script X? And a possible candidate is the following. We can take X to be LP of Z with value in some E, where this E, script E, is some LP space. So for example, you can take E to be LP of N with value in another Banach space. Let me call it Y, where Y is not some Banach space. Then our X is just LP of Z with value in LP of N with value in Y, but because these P can come together, so it's just LP of Z times, it's just Z times N with value in Y. So this is an LP space. And we have an N component here to guarantee that no non-zero operator X are compact. But there's a choice of this Y coefficient. Of course, you can take it to be the complex number. Yeah, and then you can formalize a problem there. And I can take it to be any possible Banach space. It's easy to show that its key theory is independent of choice of Z. So it's well defined, but may depend on the choice of this E, or more specific on the choice of this Y. So this is because, like for Hilbert space, all Hilbert spaces are the same. So all compact operators are the same. But for Banach spaces, the compile operator on different Banach space can be different. Although the key theory are the same, but when you do like a matrix with coefficient in this Banach space, it can be different. Okay. So this problem might be related to a choice of y. And possibly different y will give you different key theory. There are actually some known results on discussing this LP version. It kind of related to the classical work of Laforgue of the so-called Banach key theory. And quite a few works on this LP row algebra is independent of choice of y. But in our case, we actually need a specific choice of y. So just recall our construction. We start from a t that acts on this x, and we twist it by a p. This acts on the A algebra, and we go back, we evaluate it as s equal to 1. It will act on this X tensor HE, where this HE is a Hilbert space. Well, let me explain what is tensor product vector. Okay. So we expect that this composition is equal to the identity. So at least the first line and the last line are the same in the level of key theory. So to really guarantee they are the same, well, we have to deal with this extra component. So a possible candidate is the following. So we take E to be LP of N with value already in a Hilbert space. This is our Y, a Hilbert space. So X is this. And in this case, X tensor HE is a LP function with value in the Hilbert space, tensor Hilbert space. But you know the tensor Hilbert space is still Hilbert space. So this guy is the same as X. So like because we want to tensor Hilbert space, so just tensor Hilbert space so that tensor more Hilbert space does not affect the key theory. Now the first line and the last line are the same, then we can prove our theorem. So with the above choice of this module, the LP Coarse Baum conjecture holds for it. Okay, and but actually we do not know that if we use a different choice of this part y here, will still give us same result. At least for this y, a Hilbert y tells us actually the result holds, and this key theory is independent of P in particular. And there's another interesting fact for this LP version. So let's look at here the construction. We start from a T, right? And we want to twist it by a P. So this P operator acts on the value part. Okay, so maybe I just go to the next page. So this TP can be understood as T tensor 1 composed with 1 tensor P. This 1 tensor P can be regarded as a diagonal operator. Because it only acts on this part, but has nothing to do with this P part, this Z part. Roughly speaking, AIS propagation 0. But this T part, well, this is still not very complex. It's just a tensor 1. It's a tensor identity that acts on the second component. Well, originally act out here, but tensor 1 is tensor Hilbert space. For operator on the Hilbert space, we know that a tensor 1 is still a bounded operator, bounded by its original norm. But for Banach spaces, the tensor 1 is actually a little bit complicated. So this actually requires further proof. So here's a result. Maybe it's of independent interest. So I've shown the following. So suppose that you have operator T act on the LP space of some Z with value in a Hilbert space. Then T tensor 1 act on the LP space of Z with value in H tensor H. Then in this case, T tensor 1 is actually also a bounded operator, but the coefficient may not be 1. This number might be greater than 1, I call it Kg, because this Kg is the constant from the Grothendieck inequality. So actually, this is a corollary of the Grothendieck inequality, where the Kg
Do you
is
have some concrete example where the constant is that one?
Well, I call this inequality Marching-Kiewicz-Zygmunt inequality. In the original Marching-Zygmunt inequality, they prove like following: if T in B of LP of Z with no C coefficient,
Okay.
and T tends to 1 is in B of LP of Z with coefficient in Hilbert space. In this case, T tends to 1 norm is bounded by T norm.
Yeah, sure.
So in this case, the constant is 1. But in our case, well, I don't know if there's any example.
Well,
And
I would
this is
like to
really an
see
interesting
that.
question. So I will expect that this might be 1 because it's really related to classical Marching-Kiewicz-Zygmunt inequality. But I have no idea. Or maybe there's more complicated thing. Just well, doing things about binary algebra tensor product is always complicated. Yeah, but at least we know it's bounded, which is enough for our construction. We want a bounded operator, well, then that's why we know. Yeah. Okay, so yeah, this is just a technical step of our approach, and which requires, interestingly, the Grothendieck inequality. All right, so okay, sorry about I used 2 more minutes, and yeah, and thank you very much for your attention.
Okay, thank you, Jimmy. So do you have any questions or comments for Jimmy?
Yeah, I already asked my question, about this example. Just so, yeah.
Thank you.
No, it's very, very nice. Yeah. It's a very nice development. Yeah.
So the challenge is to extend to the equivariant case.
Sure. Yeah.
So here is a question: can we define it for infinite dimensional?
Yeah. Sure. Okay.
So any other questions or comments?
Just a very naive question. I'm sorry. If your metric space is not locally compact, I mean, does this row algebra give you something sensible or?
Well, maybe even a little bit better than locally compact, because well, let me maybe go back to this page. Oh, sorry about the math. If the space I wrote it here, but I didn't emphasize too much. We always assume that X is bounded geometry. So in fact, if the space X does not have bounded geometry, then this map is no longer injective, possibly. So yeah, something worse, something bad can happen. So if even it's not locally compact, I think something worse can happen.
I see. Yeah.
Yeah. So bounded geometry just means every R ball has uniformly finite points in R. Uniformly finite points for different base points. Yeah. If we do not have this uniform bound, then this map will no longer be injective.
I see. Yeah.
But so far, we do not know any kind of example of injectivity for any bounded geometry spaces. Yeah.
So this unbounded geometry example, it's a little bit mysterious in the sense it's proved using scalar curvature. So I mean, this is a conjecture which is very coarse. So there should be kind of much more down to earth approach. I believe if one finds a very down to earth approach to that kind of example, like why it's not injective, then it might provide some idea how to construct a counterexample to the Strong-Novikov conjecture in the group case. So I felt that example was not well understood, although logically there is an argument. It's a counterexample. I mean, one should not use like infinitesimal geometry. I mean, by which I mean differential geometry to give a example to injectivity. That's the argument.
I see.
So, Jimin, can I ask a question? So,
Yeah.
have you thought about any cases beyond LQ of the natural numbers or other Banach spaces?
Well, what I'm thinking is that for at least for this result, oh sorry, yeah, at least the possible generalization is Banach spaces with property H.
Mhm.
So this already contains more examples than LQ, but of course cannot go to like L infinity.
Sure.
If it holds for anything, then everything is true, but that cannot be. Yeah, but if one go to like this property H, this property will no longer hold.
Okay.
So I think it would be interesting to really find out what should be a nice replacement of this fact, this very naive fact.
Mhm.
I'm pretty sure there should be one, and at least should go to probably H Banach spaces, but yeah, might need to find out.
Okay. Yeah, thank you. So, any other questions to Jinmin or comments? So if not, let's thank Jinmin again for a beautiful talk.